Hello. Okay, I'm back for the rest of them, 9, 10, 11, and 12. So create a polynomial function with a degree greater than 3 with the following end behavior. Okay, so let's go over a couple things real quick. X to the first. This is a linear function with a positive slope. So negative x to the first power is going to look like that. Negative slope. X squared, we all know, is our friend the parabola. Y equals negative x squared is a parabola that faces down. He's so sad. The cubic is going to have 2 turning points. First power, linear, no turning points. Second power, quadratic, 1 turning point. The cubic, 2 turning points. So y equals negative x cubed looks something like this. 2 turning points. So look at the trend. When your leading coefficient is positive, you're increasing. Your arrows either face up or you're going up. When you have a negative out front, a negative coefficient, overall you're going down. So if I want something greater than 3, and I want my end behaviors to be opposite, one is down, one is up, it's going to be an odd function. So y equals x to the 4th is going to look like x squared, but just some extra turning points in there, 3 to be exact. So y equals negative x 4th is going to look the same thing, but face down. So x to the 5th is going to look like x cubed, but with some extra turning points. Y equals negative x to the 5th is overall going to be decreasing with 4 turning points. So if I want my degree to be greater than 3, like 4 or 5, I have to find which one matches my end behavior. So as x goes to infinity, which means goes to the right. So as x goes to infinity, y is supposed to be going down, and it's going up. So this one. And as x goes to negative infinity to the left, I want to be going up. Go to the left, go up. So negative x to the 5th is going to be my polynomial. Now what happens after x to the 5th? That's up to you. What's important is that you have the negative and the 5. So I could have negative x to the 5th plus 3x squared plus 7. That'll work. I could have negative 10x to the 5th plus 4x to the 3rd plus 27x. I could just have plain old negative x to the 5th. F of x equals or y equals, of course. So it really doesn't matter what happens after that. The key thing is that you have a negative leading coefficient and you have a 5th power as your highest power. It doesn't have to be a 5th power. 7th power is going to act like this too. So anything negative x to the 7th power, to the 9th power, to the 11th power, any odd power greater than 3 is going to have the same exact end behavior. Okay, number 10, graph this quadratic, show your work. I'm going to actually do part B first, because if I rewrite it in vertex form, it's super easy to graph. Sorry about that, a little stray mark. Okay, so I'm going to move this constant over to the other side, and I'm going to factor out my GCF on the right. So I have f of x plus 2 is equal to 2x squared plus 4x. Now, we cannot have our parentheses span over an equal sign. That doesn't happen. So we move that 2 over by addition first. We add 2 to both sides before we factor out our GCF. So now I complete the square. I take half of my b term and I square it. 4 divided by 2 squared is 2 squared, so that's 4. But I can't add a 4 on the other side because this 4 is actually an 8. 2 times 4. So I'm going to be adding an 8. So I have f of x plus 10 is equal to 2, and I'm going to factor this. What multiplies to give me 4 but adds to give me 4? That would be 2 and 2. This is always going to factor into a perfect square trinomial, meaning that whatever multiplies to 4 also adds to give you this 4. It's 2 and 2. It's going to be the same thing. Because our vertex form is y equals a x minus h squared plus k. So I want to get that quantity squared. So to get this into the form that I want, all I have to do is subtract the 10 back to the other side. So now I know what my vertex is. I know that my vertex is going to be -2, -10. I know it's -2 because this negative sign tells me to take the opposite of h. So I have -2, -10. I'm going to plug in values that are 2 to the right and 2 to the left of my vertex. So -2, 10, there it is. So I'm going to plug in 0. That's super easy. So I'll plug it in over here. 0 plus 0 minus 2. I get to copy it over to the -4 because a parabola is symmetric. What happens on the left happens on the right. I'm also going to plug in a -1. Yeah, it's probably easier to plug it in over here. It doesn't matter. Either one is going to give me the same answer. So I have 2, -1 plus 2 is 1. So 1 squared is 1 times 2 is 2. So 2 minus 10 gives me -8. So I have -1, -8, -3, -8, 0, -2, -4, -2. Now I'm going to do my best to draw a nice, smooth curve. That was the worst parabola I've ever drawn, but it's hard on this little pen pad. You get the gist of it. So here I am in vertex form, and I use that vertex right there. Sorry for the shift. I use that vertex right there to graph my parabola. Let's add some arrows onto onto number 11. If it was an endpoint, it would be clearly an endpoint, and it's not. It looks like it just keeps going off of the graph. So when I'm talking about an absolute maximum, or maxima, it's just a fancy word for maximum. Absolute maximum, I'm talking about the highest point ever that this graph is ever going to go. And that looks like this is the point -3, 4. When I'm talking about a relative or a local max, I'm talking about it's a maximum in that area. It's a turning point. It's when I'm switching from increasing to decreasing, but it's not the highest point overall. So that looks like it is 3, 2. In an absolute minimum, I'm talking about the lowest you ever go. I have arrows here, meaning I'm going to keep going and going and going. So there's no absolute minimum. For a relative minimum, I'm talking about in that area, it's the lowest point. It's where I'm switching from decreasing to increasing. So that point is going to be 0, -1, which also happens to be my y-intercept. I gotta pause this. I don't know if you can see it, but things keep disappearing. It's driving me insane. Hold on. For my zeros, I'm gonna have to estimate here. So this looks like it's almost at -6. So I'm gonna say like -5.90. Oh, it keeps disappearing. I see another one, looks like maybe -0.60. And there's another one right here at maybe like 1.10. And maybe about 5.20. Doesn't look like they're exactly on the graph, so I can estimate here. Okay, my end behavior. I'm talking about what y's are doing when x's are getting big or getting small. So let's start when x approaches infinity. So we have as x approaches infinity, which means as x moves to the right, what is y doing? It's definitely going down, so y approaches negative infinity. As x approaches negative infinity, we're talking about moving to the left. What is y doing? We can see as we get smaller and smaller, the y's are also getting smaller and smaller. Increasing and decreasing. We're talking about movement from left to right. So I'm going to start on the left and I'm going to trace it. So I'm going up, and then I stop at -3, x values. So I'm increasing from negative infinity until -3. At -3, I turn around. At -3, I turn around and I start decreasing. I'm decreasing from -3 until the x value of 0. Then at 0, again, I'm turning around. At 0, I start increasing again, from 0 to 3. And then at 3, I turn around again, and I start decreasing. Now don't make the mistake to write that it decreases until negative infinity. We're talking about x's, and this is getting bigger on the x's. So this is from 3 to positive infinity. Okay, last one. We are describing the end behavior of a function that has a leading coefficient of 6 and a degree of 7. So we know that an odd degree means that our polynomial is going to have its end behavior opposite. Even functions are the same, odd functions are opposite, odd degree. So a degree of 7 will have 6 turning points. Since our leading coefficient is a positive, that means overall our trend is going to be an increasing. So we're going to start down and we're going to have 6 turning points. 1, 2, 3, 4, 5, 6. Something like that. Leading coefficient's positive, so overall we're increasing from left to right. It's odd, so our end behavior is opposite. So this would be as x approaches infinity, y approaches infinity. As x's get big, where's the y facing? Up. And as x approaches negative infinity, as we go to the left, what's the y doing? Going down. Alrighty, in the second one, we have a leading coefficient of a -3. And we have a degree that is even. So negative means with an even function, like -x², that we're facing down. If it has a degree of 10, it can have up to 9 turning points. It doesn't have to have 9, but it'll be up to 9. And our end behavior is going to be down and down. So something with a degree of 10 could look like this and have 9 turning points. 1, 2, 3, 4, 5, 6, 7, 8, 9. There it is. Because of this leading coefficient of a negative, you're going to have a down, down. So this is as x approaches infinity, y approaches negative infinity. And as x approaches negative infinity, y approaches negative infinity. It doesn't have to have 9 turning points, but it'll have an odd number of turning points. Odd, so we will end down. This one doesn't have to have 6 turning points, but it'll have an even number of turning points, so we will start down and end up.